to introduce to you Kevin Cole, Harper College Assistant Professor of Geology and Astronomy. Kevin's going to talk to us about the Mars 2020 rover. It's been in the news quite a bit and a lot of great information coming. So sit back. We got a great 30-minute presentation here from Kevin. Kevin, let me go ahead and turn the floor over to you. Oh, you know what? Actually, while you're getting keyed up, I forgot to share one of these images from our club. This one comes to us. This is Gary Gall, and this is an image of Mars. Edith had mentioned earlier in one of her presentations how close Mars was over the course of the summer last year. George took this in October, and you can see the ice caps. And if you look over on the left there, you can see a little bit of the atmosphere too that's on Mars. So another fabulous picture. Gary, thanks for sharing this with us. And Kevin, let me turn it over to you.
Okay, thank you. So there we go. Can everybody see that?
Yes, looks good.
Okay. Yep, excellent.
Alrighty, so why don't we get started here. So we're going to take a look at a very ambitious mission called the Mars 2020 Perseverance Rover. Right now, this is the second nuclear-powered rover we have on the surface of Mars. And we'll talk about a little bit more about that in a little while. So let's get started. So the whole idea with Mars is that once upon a time, we think that Mars may have looked like this. We have evidence of flowing water on the surface. We have evidence of rocks that have been altered by water. But then over time, as Mars lost its magnetic field, it lost its ability to hang on to that water. Why? Because the solar wind is actually gradually eroding away that atmosphere in what's called sputtering effect. And before the MAVEN spacecraft got there, this was just a hypothesis. But now it's pretty much confirming this sputtering action by the solar wind. So we think Mars lost its magnetic field maybe about 3 billion years or so ago. And since that time, the atmosphere has gotten thinner and thinner. And with the lower atmospheric pressure, liquid water cannot exist on the surface of the planet. So it's in other locations, one of which is in the polar ice caps, and the other is in frozen reservoirs beneath the surface. So the Mars Perseverance rover is very ambitious to help add to our accumulated knowledge from all our missions that we have sent there over the past several decades. So we see that this is the target. This is a crater called Jezero Crater. And the reason why it was picked is because we are certain that this was once a crater-filled lake. During the Martian past, craters filled up with water, much like we see with a place like the Great Lakes, for example. And this is what we see here. We think this is what it'll look like maybe about 3.5 billion years, 4 billion years ago. So what we have here are basically two channels coming in. Here's an inflow channel, and here's an outflow channel. And not too many of these water-filled craters have an outflow channel, but in this case, Jezero Crater does. And from what scientists have been able to observe from orbit, they think that this crater filled in at least 2 occasions. So this is referred to as an open basin lake, since water not only entered, but also drained from the crater. So this is the region that we're taking a look at here. Here's Jezero Crater up on the top. We have actually 3 channels here. Here's the Neretva Vallis coming in, and Sava Vallis, and then Pliva Vallis is the channel exiting. With both Sava Vallis and Neretva Vallis, we have what are called deltas that are forming up, much like the Mississippi River Delta in Louisiana. And this particular delta is the target of Mars 2020. We're not going to go to the Sava Vallis Delta. We're just going to go to the Neretva Vallis Delta, and the Mars 2020 rover is right here. What makes this particular region interesting is that it's right on the edge of Acetus Planitia, which is a massive impact basin that formed about 3.9 billion years ago. And this is during what's called the Noachian period, the first period of Mars. Since that period, during the Hesperian period, which is the second period of Mars, Younger sediments filled in, maybe sediments being delivered by wind erosion and fluid, rivers coming in and filling in the basin with sediments. And some went into the Amazonian age, which is the current age that we see on Mars. These cracks right here, called nili fossae, these fractures were the result of the massive impact that created Acetus planitia, creating the stresses that created the arcs here that kind of follow the curvature of this impact basin. We also have Syrtis Major right here, which is a volcanic province. Many of you who are familiar with taking a look at Mars during with your telescopes, and when Mars is particularly close to us, Syrtis Major is kind of a big dark area that you could see through the telescope. And then we have Terra Sabea, which is a highland region. You can see very heavily cratered right here. So basically, we have a nice region where this rover could ideally, if it lasts long enough, actually sample 3 different periods of Martian history: the Noachian period, the Hesperian period, and the Amazonian period. So we'll see how the process goes on inside the crater, and hopefully we'll be able to get outside the crater and see how these other terrains compare. This is a topographic map of the area. The green right here is basically everything is measured in relationship to the average Martian radius. So the green is 5,000 meters below that, and the white is 1,800 meters above that. So we see here the red areas are, I don't know, maybe about 2,000 meters below that mean average radius. So it just kind of gives you an idea of the primary topography that's actually going from the red area down into the green area regionally. Okay, come in. There we go. Okay, so here we have a close-up view of this portion of Mars. And one of the reasons why we're going there is because we have a lot of areas here that could be environments in which bacteria could eventually have formed in, possibly. So from orbit, we know that this region has clays and carbonates, and clays and carbonates are the result of water flow. This is the delta right here. And as you can see kind of where it gets its name, it's kind of shaped like the Greek letter delta. And we're looking at this area because of many of the craters we've been viewing from orbit. This particular crater has got some really interesting features that could indicate that we might have some areas that life could have evolved in. We have a fractured surface. So we know that, when you get a fracture in the crust, water can flow down into that crack. And if it brings organic material with it, or bacteria, or very, very primitive, maybe algae organisms in there, they can actually make a living in that particular environment, especially bacteria. Bacteria can live under very, very harsh conditions, as we see here on Earth. In the lake basin itself, we have a lot of muds, and muds can be saturated with water, and that's another good location for microbes to be growing in. River sands being brought in by the channel here is another region in which you can get bacteria or other microbes inside, because you have nice spaces between the sand grains. Along the lake margin, we can wind up getting carbonates being developed. And carbonates, if you're not sure what they are, they're kind of like limestones. Well, they are limestones, but in this case, we're not going to expect to see limestones. We're probably going to maybe see a carbonate-rich mud. But we might see this along the shoreline here, along the crater rim. And again, on the crater rim, because of the original impact fracture, if those impact fractures made it down to maybe a subsurface magma chamber, maybe not directly, but enough to heat up the water, you can wind up getting impact hydrothermal systems. And hydrothermal systems are really good for the type of organisms called extremophiles, like we see in Yellowstone. And it's suspected that there might actually be an aquifer, or in other words, an underground source of water, which could also be another type of reservoir for microbes. So all these are really exciting that we could see occurring here at Jezero Crater. Here is a nice satellite view, so you can see this is the landing spot of the rover. And here we see the edge of the delta, and there's Belva Crater, and there's Neretva Vallis. Then you can see inside Neretva Vallis, this is very common to see these sand dunes. moving through here. These are actually provide a nice channel for winds that come through here and move sand around. You want to gain sand dunes that populate many of these types of channels we see here on Mars. So how do they plan to move around in this area? Well, there's a big obstacle. This big region right here in the center, that is actually a lot of sand dunes right there. It doesn't look like it, but they are. And I'm going to show you a video as this came down as it landed, and you can see it quite clearly. And the navigation system on the lander made a beautiful job in avoiding this region and avoiding a relatively rocky area off to the east right here, and landed right there. So to get to the delta itself, the rover is either going to go through the blue pathway or the purple pathway, so it doesn't cross over these dunes. And we found out with our other rovers that crossing dunes is not a very good idea, especially when you have rovers that are not moving very fast. There's not a lot of power to the wheels, simply because most of the power is going to the scientific instruments. So whichever path NASA chooses, once they get to the base of the delta right here, they're going to make their way up through one of the low channels right here, roam around up on top, and come on down, and then come around again and back up through some more channels, and then make its way up to Neretva Vallis and make its way out of the crater, and then turn left and head down south. That is the long-term goal. If the record of Curiosity is any example, I think we'll be roaming around here in this area for quite a long time. So what are we looking for? Well, one of the things we're looking for is something like this. This is called a stromatolite. This is from the Grand Canyon, and stromatolites are basically built up, rocky structures that are built up from colonies of blue-green algae. And here we have another example of one. This particular rock is about almost 800 million years old. And you see this layering that is characteristic of stromatolites. So basically, this is accounting for generation after generation after generation of these little blue-green algae that live their life in these sedentary deposits. And here's one example. This is the Shark Bay stromatolites in Australia. And these are about the only places on the planet you're going to see these around. At one point, these were all over the place, but now they're just kind of limited to Shark Bay. But you can see how these form up. They're kind of driven by the tides. So when the tides come in, these are underwater, and then the blue-green algae do their photosynthetic thing. They're little tiny plants, and when the tide goes out, they actually secrete a calcium carbonate gel that keeps them from drying out until the next tide comes in. And then generation after generation, that calcium carbonate gel eventually gets turned into limestone, and we have these limestone haystacks, so to speak, sitting right here. So this is the kind of structure we're hoping to find at Jezero Crater. This is just a cool view. This is showing, as viewed from the Mars Reconnaissance Orbiter, the actual descent of Perseverance. And this was not accidental. This was planned. We did the same thing for Curiosity, and we also did it for one of the Mars exploration rovers. This was actually not only for a spectacular image, but also confirming that the spacecraft is properly deployed its parachute, and it's making its way down to eventually land in this area. I think in relationship to this picture, it actually is over in this little saddle right there. So we're going to show you something that has never been seen before of a lander making its way down to the surface of a planet. This is a view taken from the aft shell of the rover as it made its way down to the surface. And you can see these striations right there. These striations right here are from the retro rockets of the jetpack, and just lowering this rover, as you can see, suspended by the cables right here toward the surface. So let's take a look and see what happened here.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applique indicates chute deployed.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 480 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Net filter converged. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Oh, yes, valid.
We have confirmation that the lander vision system has produced a valid solution as part of terrain relative navigation.
Timing. TBA is nominal.
We have timing of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Here in 50 Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
So that's what it'll look like to land on the surface of Mars as viewed by the camera on the rover itself and on the aft shell of the parachute, or not the parachute, but the retro rocket system. So this is actually really kind of a cool thing to see, and we'll probably see more like this in future missions. So here's where they landed. You see the scorch marks there from the rocket packs. And this is one of the early images taken by the hazard avoidance cameras. And there's the Delta right there in the distance. And I guess this video portion is, let's see if I can get that out of the way. There we go. So now we see, this is what it would have looked like if you were standing there. It was a very gentle touchdown without any problems at all. So what's going on here with Perseverance? Well, this is the mission of Perseverance. It's going to take a look at the local geology, study the rocks, landscape, the landing around the landing site, take a look at the region's history, how often was that crater flooded, what kind of sediments were laid down in, what's the geochemistry of those sediments, etc. We're going to take a look at the potential for astrobiology, determine whether that area of interest was suitable for life, and look for signs of ancient life itself. As we've seen in other locations on Mars, the geochemistry would suggest in some areas, like in Meridiani Planum, the water might have been too acidic, but at Jezero Crater, it looks like the water is just right. Not Jezero Crater, but Jezero Crater. Looks like the water was just right. So that's what we're going to take a look here. We're going to compare those conditions with those other surface activities. They're going to do something special called sample caching. They're going to be taking drill core samples and they'll store them on the rover, and then the rover will come back to very specific locations and drop some samples there. They'll do this at about 2 or 3 sites in preparation for a future sample return mission. And of course, the whole thing is designed to prepare for humans and test technologies that we'll talk about in a moment. Here we see some of the instrumentation. We have spectrometers for taking a look at surface geochemistry. We have ultraviolet spectrometers for taking a look at organic molecules on the surface of this particular area. We've got our own weather station. We have a supercam that's got a laser on it that will vaporize rocks, and we can. There's also a spectrometer in here that'll measure the elemental characteristics of what was just vaporized. And this has also got a high resolution camera. We have the Mastcam cameras that gives us stereo views. And we've also got a special instrument called RIMFAX. And what they're going to do is they are going to send radar signals down into the surface and see what kind of layering is down there. Maybe see how deep water ice is. This is something that's never been done on the surface of any kind of a planetary body directly. MOXIE is producing oxygen. I'm going to show you the results of that in a moment. And tucked underneath the rover is this little guy right here called Ingenuity. Now, one thing that's kind of interesting about this, we have some new technologies on this rover. We found out with curiosity that the rover wheel designs were not quite up to the task, although it's been roaming around for about 12 years now, but holes have developed in the wheel. So this one is made of material that should be more durable. The wheels are narrower and they're in greater diameter, so this should weather the surface very nicely. There is a microphone on this rover, so we can hear what the sound of Mars is like, which I'm going to show you in a moment. Our collection of rocks, what's called caching, will be conducted throughout this mission, and MOXIE will be taking the first steps of producing oxygen from Martian atmosphere, which is primarily carbon dioxide. And as we're speaking, this particular activity has already been conducted, and it was conducted quite successfully, as we see right here. This was the warm-up period for a couple hours, and then we could start seeing the production of oxygen. So this is basically a mechanical plant. It's taken in carbon dioxide. There's a lot of carbon dioxide on Mars. That atmosphere is 95% carbon dioxide, and it's taken in that carbon dioxide. It's breaking down the carbon and oxygen molecules and taking away an oxygen atom and releasing carbon monoxide back into the atmosphere. And during this production period, it produced almost 5.5 grams of oxygen, which is just about enough to keep an astronaut alive on the surface for about 10 minutes. This is an important technology demonstration here, because this is the type of technology we'll need if we're going to start sending up settlements on Mars, because now we can start producing our own oxygen, which can be used for life support and it can be used for fuel. And we don't have to worry about carrying oxygen with it or importing oxygen from the Earth, because that gets very, very expensive. So a highly successful experiment. And I think they're probably going to do this a couple more times just to make sure they got some good data on it. So this was already completed. Now, I hope you can hear this. But what you're hearing in the background is the wind on Mars. Never before have we heard anything from another planetary body. So this is from the microphone that's on the rover. And here we see Ingenuity, the rover looking at it, make sure he's okay over there. And on this first test flight, this is actually from the second test flight. That's the shadow. Kind of looks like a dragonfly. But I'm not going to show you just a shadow. I'm going to show you the whole thing. The left here is the flight on the 19th. The right here is the flight on the 22nd. The first flight rose to a height of about 3 meters, hovered around for about 30 seconds or so, and then came on down. The second flight hovered up to about 5 meters and stayed up nearly a whole minute. And it did some maneuvering. Both of these did a little bit of maneuvering to test their capabilities. This particular video I have on the right here, they didn't have the data yet to show the helicopter landing, but it did land safely. And the height that we see that this helicopter is at on the second flight, about 5 meters, that's about as high as they're going to go with this. This has a range of about 980 feet, or about 300 meters or so. And they're getting ready for the next step, flight number 3. Flight number 3 will be a little bit more ambitious. They'll be moving sideways and back and forth, maybe about 8 meters, and maybe take some images like this. Here's the first aerial image of Mars. There is the shadow of the helicopter, and there are the landing legs, and you can see the tracks left behind by Perseverance as it was setting up to deploy this helicopter and then back off. The rover is about 200 meters away from the helicopter. Don't want to put the rover in danger in case something goes wrong and it goes a little haywire. So we want to make sure the rover was well out of its way. But this is showing to be a highly useful demonstration because not too far down the road, we are going to send a helicopter to Titan, the largest moon of Saturn. And that mission is going to be called Dragonfly. And we hope to deploy a helicopter on the surface of Titan and fly around in that denser atmosphere with a little bit less gravity than what we see here at Mars. So this was an important technology demonstrator. And if it continues to work well, we might even see a few dedicated aerial systems flying through the Valles Marineris or maybe some other of the volcanoes that we see on the surface. So eventually what they want to do is take the helicopter and maneuver it around an area maybe the size of a football field or so, take images along the way, test the camera, and get a good feel as to how this flight will work. These blades are about 4 feet in diameter. So because of the very thin air of Mars and the low gravity, these helicopter blades have a greater angle of attack than what we would see here with an Earth-based helicopter. And they're counter-rotating, so there's no uncontrolled gyrations of the body of the spacecraft itself. And we have a camera on the bottom right here. So this is very simple. All it's going to do is take some pictures, communicate with the rover, but hopefully it might last long enough to move along with the rover in its exploration of this area. This is solar powered. There's a solar cell on the roof of this helicopter. So, so far, so good. Here is the target. And you can see right here, see this gray area right here? Those are sand dunes. We don't want to go through that. So we're going to go around it. And as we get over to this side, we're going to start getting a close look at the layered deposits right here, all deposits that have been deposited by water. So we're going to see things like silts and clays and sands in here and see how they compare with the silts and clays and sands that have been observed by Curiosity. Right along the back here, here's the crater rim. And this is the entry of Neretva Vallis into Jezero. And eventually the rover is going to make its way up to the top of the delta right here and make its way up that canyon and head out south and see what's out there. It's going to be a while before we get there, but that's an overview of what this area looks like. And the rover has the imaging on the rover is quite remarkable. It's actually a little bit better than Curiosity. As a matter of fact, Perseverance can actually move a little bit faster than Curiosity. And to give you an idea, this is one of the first pans that have been returned. And that little rock out there is zoomed in. You can see a nice detailed description. They call it a seal because it looks like a seal. And this is called a ventifact, and this was carved out by the Martian winds. The Martian winds really are not that strong because the atmospheric pressure is only about 1% that of the Earth. This is a kind of wind erosion that takes millions of years to accomplish, but there it is nonetheless. And here we see the panorama. This is a 360-degree view panorama. There is the delta right there, about 2 kilometers away. There's the crater rim, and there's the channel opening from Neretva. And you can see all the way around the crater rim right there. So this is what the surface looks like. Again, there is the thrust remains of that jetpack. The jetpack is probably over to the south right here somewhere as it crash landed. So a lot of interesting things to see here. We'll be taking a look at some interesting rocks along the way, no doubt. We think we have already spotted a couple of iron meteorites on the surface, but we're not really sure yet. They look a lot like some of the iron meteorites we've seen elsewhere on the planet. So what we have here, this is the family of surface missions that we have on the surface of Mars. Of course, Viking 1 and Viking 2 were the first time we landed, that NASA landed missions on the surface successfully. The Soviet Union did land a few, 2 or 3 on the surface, but they landed during a global dust storm and they were not successful. But Viking 1 and 2 landed after that dust storm and were operational for 7 or 8 years, maybe 10 years or so before they shut them down. Pathfinder was a technology demo for a rover on the surface of the planet at Ares Vallis right here. Here's Opportunity, that was at Meridiani Planum, and Spirit, that was over here at Gusev Crater, and Curiosity at Gale Crater. Here's Insight, that has taken the seismic pulse of the planet just a little bit north and west of Curiosity, and there's Perseverance right there at Syrtis, just on the edge of Syrtis Major. So you can see Syrtis Major very clearly right here. And this is something that's very easy to see with amateur-sized telescope. So with all the talk of Curiosity, let's not forget, I should say Perseverance, let's not forget Curiosity is still roaming around on the surface. It's been there for 12 years. I kind of find that hard to believe, but it's been there for 12 years. It's covered 15 kilometers and it's still operational, shows no sign of slowing down. And of course, we have Mars Insight. This is Mars Insight. This is a static lander, and it's basically taking the seismic pulse of the planet. We tried to deploy a heat probe sensor on here, but it didn't quite work out that way because the soil was not behaving the way we thought it would. But the seismic instrument is operating nicely right here. This is before it was deployed up on top here, so it's been deployed by the robotic arm. And it's been collecting data since 2018, and it's recorded earthquakes anywhere from 2.2 to maybe about 3.4 magnitude. So we're getting a good look at what's going on the interior of the planet. So it's always fun to leave off with a little cartoon here. These rovers tend to get very attached to their operators, and there's always kind of fun to take a look at some of the cartoons that they come up with. So that is the presentation. So if you have any questions, I'd be happy to take them.
Having a great presentation, a lot of detail. It's just amazing the extent of exploration that's taken place on Mars.
Yeah, it's really impressive, and it's an exciting time right now. Let's not forget that in addition to NASA, the Chinese have an orbiter, and they will be deploying their lander probably this summer. United Arab Emirates has an orbiter there as well. And of course, the Europeans also have their orbiters. So it's been a very, very busy season, so to speak, for Mars as far as robots go.
Sure has. I think the most exciting, well, you know, aside from the, I'm forgetting the name of the helicopter, but converting that carbon dioxide into oxygen, that's incredible.
Yeah, that was an important experiment. So now we know that it's the technology is doable, and I'm sure in future missions we'll see larger versions of that being deployed.
Yeah, absolutely. Any questions for Kevin? Just a reminder, go ahead and make sure that he's listed in the to column. Click the drop-down box, type a K, and you'll get to his name. You can go ahead and type a question to Kevin. We'll give you just a minute to do that. Now, Kevin, what's the next planet that they're looking to deploy another helicopter?
They want to deploy one at Titan, which is the largest moon of Saturn. As you know, Titan's got a very, very thick atmosphere. It's actually 60% thicker than our own atmosphere, but its gravity is probably comparable to that of the moon. So that'll be another very challenging type of mission. And this is a really nice technology demo for this.
Yeah, that's a mission they're talking about launching. Is it 2030?
Yeah, I think that's the general time range.
Yeah. Well, I don't see any questions. Kevin, do you have any in your chat?
Let's see, where do I look?
You go down to the bottom, you'll see the banner appear, and just click chat.
Let's see. Oh, okay. So we see a question from Deepak Patel. How much can the rover move in a day? Well, it's kind of hard to tell. It's going to move at about the same rate as you walk. And the nice thing about the rover is we don't have to worry about the sun being up because these are nuclear powered. So we can move anytime we want, but we don't have headlights, so we're not going to be moving at night, obviously. But you could see with Curiosity, it moved about 15 kilometers in 12 years. So it's like 1 kilometer per year. But understand too that they're not just moving; they're stopping and observing for months at a time. So it's it can move, maybe a few hundred meters a day.
Kevin, what was that? What's the distance when you were showing the crater rim and as it exits the crater and heads south? What is that overall distance to get to that point to exit the crater?
That's I think it's about 7 or 8 kilometers. It's doable. I mean, Curiosity has been doing it, so this is definitely a doable type of target for them.
But it could be multiple years before we see
Oh,
them.
definitely. Yeah, I would see so. They're gonna concentrate all their activity around the delta right now because that's where the water was depositing sediments, and that's the type of environment in that region that you would expect to see some kind of maybe biology going on or chemistry leading up to biology, and that's what they're looking for.
Any other questions for Kevin? I don't have any in my chat. Kevin, do you have any others?
Yeah, here's a question from Adriana. How long is the rover going to stay on Mars? The rover is going to be there permanently. These do not come back, but someday, manned missions will go there and they'll find these rovers there and they will probably study them. And to give you an idea how big they are, the rovers are about the size of a small car, maybe a little bit smaller than a Corolla. So these are massive rovers, the largest rovers that have ever been deployed. And they've done so highly successfully. So they're going to stay there for good.
Kevin, thank you again. Fabulous presentation. And, we appreciate the partnership in hosting Astronomy Day with you guys and certainly the first ever virtual Astronomy Day. So thanks.
Yeah, it's been quite a challenge, I can see. Okay, thank you.
All things are going well, though. But thanks again, Kevin. All right, Wally, let me turn it over to you.